So obviously, all of us are very used to thinking about the fact that we have to think about data analysis at the same time that we're thinking through experimental design. This is equally so, obviously, in the context of computational modeling. It's not impossible to take an experiment that was designed not for computational modeling, maybe for statistical analyses, and develop a computational model for it. But a lot of the experimental considerations that get optimized for statistical analyses don't necessarily translate perfectly to modeling. And so I just wanted to bring this up. So one of the things that really is very different is that in statistical analyses, often what you're looking at are values. Are values higher or lower in some statistically significant way? And in the context of computational modeling, what you're going to be doing is creating an ODE system. So this is a dynamical system that's going to have to evolve over time. In order for you to create this system, you're going to want to be able to test that the model is actually accurate. And so you want to think about it as, okay, what ideally is my model producing? And is my experiment set up to actually test that this model is correct? So if you go back to this glucose insulin model that we started with, you'll notice that if you just simply think about values, many of these different disorders look potentially functionally identical, especially if you consider just a single time point. So if you're looking really just here, these two are going to look very similar. And it's only when you consider the dynamics that these disorders start to look different. So the first thing to mention is that even though it's very common to take a single measurement, in the context of developing a computational neuroscience model, what you're going to want are to collect continuous measures, ideally over multiple components of the circuit. So at the bare minimum, if you have something that involves, let's say, a negative feedback loop, you would definitely need to collect a signal at both the excitatory and also the inhibitory components of that negative feedback loop. So I know this is challenging for people, for example, who are doing electrophysiology and for whom, inserting an electrode is a very big deal. But picking those areas strategically becomes very important. Even better if you can measure, at more than 2 places and actually as many places as possible, the better the coverage you have over every one of these components, the better you're going to be able to resolve the dynamics and also causality. The second point is, well, okay, so in line with this, you see that just measuring one value here is actually not going to be enough to discriminate between these disorders. So you want, again, to measure across different components. You want the dynamics, and also you need to consider that because you're going to be focusing very deeply on the dynamics, averaging time series can be potentially a problem because you're going to wash out your dynamics to some degree. And so for that reason, if possible, you want to maximize your SNR, your signal to noise ratio, over long data rather than low SNR over short data. And that actually goes against some of the principles that are used in some of these, in neuroimaging, these huge data sets like UK Biobank, where you have, very short resting state data, but over huge amounts of, huge numbers of people. And the assumption is that having lots of people sort of makes up for the fact that the data quality for each individual is not as good. The other thing you might want to consider is that one of the advantages of computational modeling is you can design what I call a critical experiment. What you want to be able to do is to set up your model to consider potentially competing hypotheses. So very often in neuroscience, there are many competing ideas about how the circuit is set up, what their functions are. And the beauty of modeling is that you can model each one of those competing hypotheses and ask what their outputs would look like dynamically, and then see where those outputs maximally diverge, and then design the experiment to measure exactly where they maximally diverge so that you can discriminate between those competing hypotheses. This is a very powerful way to use models. So again, not even if you say, okay, I don't have enough information about the system to be sure about how this model is set up, even being able to set up a provisional circuit with lots of different ways of doing it. In principle, you could look at all the combinatorial ways that the circuit could be set up and ask what those outputs would be, and then let the data tell you which of those configurations are compatible with the data and which ones are not. And then the other advantage of the model from that perspective is that you can perturb the circuit in silico. You can ask what would happen if I were to stimulate the circuit here versus here versus here. How would it affect the dynamics? So again, you can do these in silico experiments that then can create testable hypotheses, which can then be tested. My last point is that if you're going to take advantage of the multiscale capabilities of NeuroBlox, you want to make sure that you validate these by also collecting data across multiple scales, and ideally simultaneously, so that then you can develop the transfer functions that allow you to ask, how do you get from the bottom layer to the next layer, to the next layer, to the next layer? So again, I'm not saying that these are easy experiments to conduct, but it's something to consider if your ultimate aim is to create a rigorous model.